Well, welcome back, everybody. This is week number 7. As you know, next week is the final week. On the 22nd will be our final. Let me see what can I say. The plan, as I said in my email, is to knock out these next 2 days, Tuesday and Thursday, knock out 13, 14, and 15. 14 and 15 are relatively short chapters, so it won't take very long. And then on Tuesday, if needed, finish up the last chapter. A reminder, chapter 16 will not be on the final, but there is homework for chapter 16. Reminds me, remember that of all the homework, the lowest 3 homeworks get dropped. And so they're not incorporated into your final grade. So from your end, they may look like they're not graded or they just don't count. So remember, that's the lowest 3 get dropped. Let's see what else. I think that's it. Any questions? It's been fast paced, believe me, even from my end. Normally, like I stated, week 7, we're probably just getting into maybe a third of the semester, and here we are finishing up in the summer. It's quite intense, and it's even more intense, I think, for face-to-face, because you'll have the actual lab to do and have to go through that. So at least here, the online lab got time to get it completed and not be governed by the 3.5 hour time limit in the lab itself. And so it has its pros and cons, Anyway, I just got noted that I guess at least at GCC, we're going back to face-to-face come spring 2022. I've not heard from SEC yet. I know some classes are going back, face-to-face this coming semester, but some are still online. So we'll see how it goes. Anyway, let us begin. Chapter 13. An interesting word here called stoichiometry. Big old fancy word for something you already began to do, and that is when you balanced the chemical equations, okay, those coefficients in front of the chemical equations are ratios, okay? And so if we have a ratio of, let's say, 1A plus 2B to give us whatever, maybe 3C, whatever that chemical is, that stoichiometric relationship between A and B is a 1 to 2, okay? And we get that from a balanced chemical equation. So that's why it's so important that when we have an equation, that we make sure we start off with a balanced chemical equation. Also, with this scenario is that we are still working with moles. Moles is the common unit between chemical reactants and products, between apples and oranges. I keep using that as an analogy, but that's the best analogy I can utilize it. I cannot go directly from an apple to an orange unless I go through moles. Okay, and that's just an analogy. I'm not saying for reals apple and oranges. I'm just saying I can't get from chemical A to chemical B without going through the units of moles. So I need to refresh my memory on how to calculate the molar mass, which we did in the previous chapters. Okay, adding up all the atoms in the formula. And then that molar mass has the units of grams per mole. Remember the atomic weights on the periodic table. All the elements have an atomic weight, and the units for those elements is grams per mole. Okay. And then we get the reaction, we balance it, we get the stoichiometric relationship, and now we have that ratio. Just like the stoichiometric relationship between a bicycle and the number of tires is a 2 to 1, right? And it's 2 tires for 1 frame, or a tricycle, 3 tires to 1 frame, that's a 3 to 1. Or a unicycle happens to be a 1 to 1, 1 frame to 1 tire. That is stoichiometry, okay? Except now we're going to, in the car is obviously 4-to-1. Now, sometimes a relationship is 2-to-3, 4-to-5, whatever our balanced chemical reaction gives us, okay? So stoichiometry. So if we look at this reaction of nitrogen oxide in the presence of oxygen, it gives us nitrogen dioxide, okay? We balance it, requires 2 NOs, 1 oxygen, and 2 nitrogen dioxides. So what we say is, okay, it takes 2 molecules of NO to react with 1 molecule of oxygen. Okay, now remember, 1 molecule of oxygen gas is diatomic. Okay, so there's a 1 in front of the O2. Okay, it's not saying 2 molecules of oxygen, the oxygen atom. So 1 molecule of oxygen, which gives us 2 molecules of our product, okay, NO2, nitrogen dioxide. Now, that stoichiometric relationship is a 2-to-1. So if we start off with 10 molecules of NO, then we require 5 molecules of oxygen, which then will give us 10 molecules of NO2, okay? Now, we can replace the term molecules and go right into moles, because that's what we're really dealing with here, okay? That we can say that 2 moles, and remember, 1 mole is equal to 6.02 times 10 to the 23rd atoms or molecules of NO, okay? So if we have 2 of those, 2 moles of NO require 1 mole of oxygen, which then gives us 2 moles of our final product. In the bottom reaction, we have nitrogen plus hydrogen gives us NH3, good old ammonia. So when we balance it, we end up with 1 molecule of nitrogen, 3 molecules of hydrogen gas, okay, which then gives us 2 molecules of our final product of ammonia. And it's balanced, okay? We got 6 hydrogens, excuse me, on the left-hand side, okay? Let me mark these so we make sure we follow where we at. Okay. Do we not have a total of 6 hydrogens here? And over here, we got a total of 6 hydrogens. Over here, we got 2 nitrogens, and in the product side, we have 2 nitrogens. So we are balanced. We are balanced. So what that tells us, instead of substituting the word moles, that we have 1 mole of nitrogen requires at the minimum 3 moles of hydrogen gas to give us 2 moles of the final product of ammonia. This stoichiometric relationship between the reactants is a 1-to-3, of which I can write this ratio, and we're back to a ratio, right? Where I can write with nitrogen in the numerator and hydrogen in the denominator. Or I can invert it. 3 hydrogens on top, 1 nitrogen in the bottom, okay? Which one I use depends on the question being asked and what I'm calculating. Obviously, if I'm looking for nitrogen, and I'm looking at the relationship between nitrogen and hydrogen, I'm trying to calculate how much nitrogen I need. If I start off, let's say, with 6 hydrogens, I would use the one on the left. Why? Let's say I have 6 hydrogen molecules of gas. Well, I would multiply by this unit on the left, this ratio, because I'm looking for nitrogen. So notice my hydrogens cancel out. I require 2, 6 divided by 3, 2 moles of nitrogen. Okay. Just like the conversion factors we did way back when, okay, I stated, let's set up your ratios like this with these units, dimensional analysis, and follow your units. Here we are, we're at that point. Follow your units, okay, because it will help you to set up the proper ratio in the proper manner to get to what I'm trying to, you're trying to calculate. Okay, so coefficients from the balanced chemical reaction, okay, gives us these mole ratios. Excuse me. My earpiece is acting up. All right, let's take a look at this reaction. We have iron 3 oxide reacting with carbon monoxide, which gives us iron, elemental iron, plus carbon dioxide. Okay, so we go to balance it. We end up with one molecule, 1 mole of iron 3 oxide, 3 moles of carbon monoxide to give us 2 moles of iron and 3 moles of carbon dioxide. Okay. So we have 2 reactants, 2 products here. Okay. Now let's look at the ratios that we can use if we need it, depending on the problem. We have the relationship between iron and carbon monoxide. Okay, a 50 iron relationship in yellow. So that ratio is 1:3, which we can write in this way or this way, depending on what we're looking for. But we also have a ratio between the iron 3 oxide and iron. Okay, this is a 1:3 ratio. The iron 3 oxide to iron, that's a 1:2 ratio. Okay, and from iron 3 oxide to carbon dioxide, that's another one. That's a 1:3 ratio. So right there we have 1, 2, 3 ratios that we can write 1 or 2 ways. That's a total of 6 ratios that we can write. Okay, now that's just looking at carbon 3 oxide. Now we can also have the relationship between, I will change it to a different color. Let's make this one green, for carbon monoxide to iron. Okay, that ratio is 3:2. Okay, we already have the carbon monoxide to iron. Okay, and then carbon monoxide to carbon dioxide. That's a 3:3 ratio. Or isn't that simply a 1:1? Same thing, right? And then finally, if needed, we can look at the ratio of the iron to carbon dioxide right there. And that's a 2:3. So the takeaway from here is this: once we get we can have the words written out. Iron 3 oxide in the presence of carbon monoxide reacts to give you iron and carbon dioxide. So that could be written in words. So your job would be to take those words and write the formula. Okay, so we're saying iron 3 oxide gives you Fe2O3, carbon monoxide CO, iron obviously Fe, and carbon dioxide CO2. Okay, then we balance it. Well, after we balance, we end up with the coefficients. Once we got a balance, recognize the ratios between reactants and products. Okay, doesn't mean you're going to use them all, but it does mean you may use at least one of them. Okay, because what happens is occasionally you might end up with a scenario where you are asked to, if I need to make, for whatever reason, 10 grams of carbon dioxide, how many grams of iron 3 oxide do I need to start off with? Okay. Or I'm getting signals that my internet is acting up again. Or you might be asked the question, all right, what if I start off with 5 grams of carbon monoxide? How many grams of iron will I make? Okay. And those are the type of questions we'll be asked. All right. Now, once you're asked and you identify who you are working with, then everybody else in the party is not important, so to speak. Okay. You're only concerned about what the question is asking you. Repeat the question. Oh, okay. Yeah, I'm getting signals that my video is kicking in and out. My internet connection is being intermittent. All right. So the question here I wrote in yellow was, if I need for some reason to create 10 grams of carbon dioxide, which I highlighted in yellow, the question may be, well, how many grams of iron 3 oxide would I need? So on the far left, I put a question mark. I need to calculate how many grams of iron 3 oxide. And also in that scenario, I see that my ratio from carbon dioxide to iron is a 3:1. Okay. So I got to recognize first who I'm working with respect to what the question's asking me. And so in this question in yellow, I wrote here, carbon dioxide and iron 3 oxide. Those are the guys I'm worried about. Don't care about carbon monoxide, do I care about iron? We assume that there is sufficient amount of money, amount of material to create whatever product I'm trying to make. So once I've identified who I'm working with, then identify the coefficient. Okay, because notice I start with 10 grams of carbon dioxide. I need to convert that to moles. So I need the molar mass. And for moles, using the stoichiometric relationship 3:1, that gives me 2 moles of iron 3 oxide. And then for moles of that, I get 2 grams from the molar mass. And I have at the end a flow chart that kind of puts everything together. Recall the previous flow chart we had. The one we're going to give you here is even more, encompasses not only the STP scenario with gases, but this scenario here. All right, so let's look at the problem. So we got the reaction up here. The question is number 1, how many moles of iron can be formed from 10.2 moles of carbon monoxide? So identify what you're looking for. We're looking for moles of iron, and we're starting off with 10.2 moles of carbon dioxide. So going to the reaction, my only concern is carbon monoxide and iron. So if I start off with 10.2 grams of carbon monoxide, how many moles of iron do I need? All right. And so that's the only 2 I'm concerned about. Don't worry about in the question, iron 3 oxide or carbon dioxide. We're only concerned about carbon monoxide and iron. Identify the ratio of 3:2 between the 2. There's 3 carbon monoxide, 2 every 2 irons. Okay. And so once I do that, I write down what I'm given. Always, in the dimensional analysis, what am I looking for? 10.2, what am I given? 10.2 moles of carbon monoxide. Obviously, I'm going to have a conversion factor of some sort. And what am I looking for? I'm looking for moles of iron. Okay, so by writing down what I have and what I'm looking for, that helps me direct me to my conversion factors to get me to my answer. So obviously I need a relationship. So I'm only talking about iron and carbon monoxide. This stoichiometric relationship, I would put here my conversion factor. Since I want iron as my answer, guess what? Iron goes in the numerator, carbon monoxide goes in the denominator, okay? And their corresponding coefficient. Check my units. Notice that carbon monoxide cancel, leaving me with units of iron. So you see how we went from apples to oranges here? The apple is carbon monoxide, the orange is iron, and the only way to get to carbon monoxide from carbon monoxide to oxygen is through moles. Okay, now here we start off with moles, but the problem could be when you're going to see down the road that you may be given the problem in grams. Instead of having 10.2 moles of carbon dioxide, you're going to have 10.2 moles of grams of carbon dioxide. Okay. That's not a problem, okay? Because now you know about the molar mass, because from the molar mass of that, you convert those grams to moles. All right. Let me clear this up. And so that's our factor. So for 10.2 moles of carbon monoxide, I would create in this reaction 6.8 moles of iron. Okay. And this stoichiometric relationship is true whether I make the quantity in the lab, meaning grams, or I have an industrial chemical plant and making this in tons. That same stoichiometric relationship is true. Okay. All right. So we will go through the calculations of very similar, except the numbers obviously would be bigger if a chemical engineer was working, trying to figure out how much I want to make tons of iron. All right. So the next one now is how many moles of iron 3 oxide are needed to form a 17 moles of carbon dioxide. So we're looking at 17 moles. We need to make 17 moles of carbon dioxide. Okay, and we need to know how many moles of iron 3 oxide are necessary to make those 17 moles. So our only concern is between the stoichiometric relationship between iron 3 oxide and carbon dioxide, which is 1 to 3. Okay, so I marked that on my balanced chemical equation so I can keep track of where I'm going. Notice here that my units cancel if properly set up. I forgot to check them off here. Notice monoxide cancels. In this case, carbon dioxide cancels. Okay. And so you can see that ratios are 1 to 3. So whatever I start off with the amount of carbon dioxide, I should need 1/3 of that. Okay. Which is from 17 moles of carbon dioxide, I would need 5.7 moles of iron 3 oxide, okay, to make that amount of material. Now, again, yes, I know carbon monoxide is involved, but when we do these calculations, we're only concerned about what the question is asking us. We assume there's sufficient amount of carbon monoxide to give us this reaction, okay? And generally we would, when these, in reality, what happens, one of these reactants is in excess. That assures that we get the right amount of material of product that we're trying to calculate. All right, so look, let me clear this up. So for these type of calculations, one, you need to have a chemical reaction, obviously, and must be balanced. Identify the mole ratio between reactants and products, okay? You're asked a question, identify what you're looking for and what you're given. Pick the correct mole ratio and just simply do the math. Okay, check your units, make sure things cancel off properly, and then you're done. Now, right now, we only have one conversion factor. But like I said, right now we're starting with moles. But in reality, we don't start with moles in the lab. You know, our balances don't weigh in moles. They don't measure in moles. They weigh in grams. And so we would have to actually start with grams and then convert that to moles, that reactant, and then use the mole ratio of the chemical reaction to give us moles of what we're looking for. And then from that, its molar mass, we will calculate how many grams that corresponds to give us an answer. The net result is this, that you will end up at the minimum with at least 3 conversion factors. Okay. And this is also what I stated back when we were doing conversion of units. You would have at least 3 conversion factors. Okay. All right. So let's do this one. Here you're given a reaction of sulfur dioxide plus oxygen to give us sulfur trioxide. Okay. So we can add a 2 there because I can maybe, you know, this one here, I got to play with the numbers. If I add a 2 at sulfur trioxide, I get 6 oxygens and 2 sulfurs. Well, if I put a 2 in front of sulfur dioxide, that balances my sulfurs, results in, by default, my oxygens get balanced. I end up with 4 oxygens from sulfur dioxide. I got 2 in oxygen. That gives us 4 plus 2 gives us 6. So we are balanced. Okay. So first question is this: how many moles of sulfur trioxide, so we're concerned about sulfur trioxide, will form if I have 0.165 moles of oxygen. So we're only concerned about oxygen and sulfur trioxide, okay? Which happens to have a stoichiometric relationship of 1 to 2. Now, remember, we don't have to put a 1 in front. It's understood to have a 1 there in front of oxygen. Unless you're on doing homework or something, you would have to select a 1 for a 1 in doing homework or some assignment on Canvas, okay? Unfortunately, because Canvas doesn't understand that. All right. So those are the 2 reactants we were concerned about. We identified them, and so we set up our problem. We are given, let me do this. We're given 0.165 moles of O2, and we're going to get or determine how many moles of SO3 I need, okay? And so from that, O2 is going to be in the denominator, SO3 is going to be the numerator. So, that's SO3, not 4. It's 2 to 1. Note my oxygens, okay, they cancel out. So I need to take my 0.165 and simply multiply by 2. And therefore I have 0.330 moles of sulfur trioxide. All right. Next problem, how many moles of sulfur dioxide? So we're looking at sulfur dioxide needed to make 0.042 moles of sulfur trioxide. So that's only concerned about those 2, okay? And as we did do before, we write down what we're looking for. And my internet connection is still acting up from my end. Sulfur trioxide. Okay, I also noticed that my resolution on my pen is very, very good. We want sulfur dioxide. Okay. Sulfur dioxide, sulfur trioxide. We set that up. And it's a 2 to 2, right? Or a 1 to 1. Same scenario. But until you're comfortable with that, if it's a 2 to 2 ratio, just put the 2s in there until you become comfortable with the whole scenario, and then you can recognize right away it's a simple 1 to 1. Okay, but until then, just maintain the 2 to 2, the coefficients. And so that means that I'm going to make 0.042 moles of sulfur dioxide. All right, I'm not going to make it on so much I need. It's just simply a 1-to-1 relationship there. Okay, so rehash again. You got the chemical reaction. In this case, it was given to you, but it could be written in words. You take those, break it into a chemical reaction, balance it out, identify the ratios between reactants and products, and then using those ratios, you are given the problems, and then you just set it up properly with the proper units so they cancel out, follow it through, and you're at where you're going, where you need to go, depending on the question. And so here in this scenario, all these problems here we've been doing, we're given the question is given to you in moles. And I said earlier, we're starting with moles, but in reality, we need to start with grams because that's what we weigh out in the lab. And so this brings us to a molar mass, because from the molar mass, we can calculate the moles. So here's a beginning of the flow chart that we're gonna eventually give you, combine the 22.4 liter scenario at STP. So if you are given something in grams, and this is already the assumption here that you have a balanced chemical reaction, okay? So before you can do any calculation, you're going to make sure you have a chemical reaction, and you're going to make sure it's balanced properly, okay, with the correct coefficients. So once you have that, now you can do your calculation. So you could be given grams and that's whatever you're given, whatever you're trying to calculate. You have to start with grams. From the molar mass, you're going to divide by the molar mass to give you the moles of what you are given in the problem. From the mole ratio, which is the coefficient of the balanced chemical reaction, you're going to determine the moles that you're looking for the reactant, for the product, or whatever you're trying to calculate, just like we did earlier. So what we've been doing at this point, up to this point, we have been in this section right here only. Moles given, we got the mole ratio, we go looking for whatever moles. We're extending it now, okay? Because now we're going to extend calculations that are done in reality using grams, okay? So moles given and the molar mass gives us the moles given. And to refresh your memory is if I take the grams given and I divide by the molar mass, I get the mole. And when I get the mass, and if I multiply by the molar mass, I go back to grams, okay? Grams to moles, I divide by the molar mass. Moles to grams, I multiply by the molar mass, okay? And you forget that, remember the units of molar mass, grams per mole. So you can write that ratio with grams in the numerator, or invert it where you got moles over grams, okay? But notice that if I got moles, if I want grams, and I get 2 moles, I divide. So this is grams given right here. So this would be this scenario. And if I got moles, I'm going to get back to grams. Okay, it is this scenario right here. See that? So keep track of your units. So here we have a reaction where we have iron to oxide reacting with aluminum to give us iron plus aluminum oxide. Okay, aluminum oxide, not aluminum, not dialuminum trioxide. It's an ionic compound, no prefixes. Okay. And after it's balanced, 3 moles of iron to oxide require 2 moles of aluminum to give us 3 moles of iron plus 1 mole of aluminum oxide. Okay, so a couple of problems. First problem will be calculate the mass of iron 2 oxide needed to react completely with 5.5 grams of aluminum. And so we are simply looking at the reactants. That's it for that problem.